Is going to be an introduction to the evolution of stars. Stars are fascinating celestial objects that have provoked humanity for centuries. They are source of light, heat, and life as we know it. In this presentation, we will explore the process of how stars are formed from their birth in a nebula to their eventual fate as a white dwarf, neutron star, or a black hole. Stellar evolution is the process by which a star changes over the course of time depending on the mass of the star. It's a complex and fascinating process that spans millions of years. So let's start by asking, where do stars come from? All stars are formed from collapsing clouds of gas and dust, often called nebulae, or molecular clouds which serve as the birthplace of stars. Nebulae have a typical density of about 100 particles per cubic centimeter, with a mass of about 6 times the mass of the Sun and a huge radius of 10 to the 14 kilometers. Nebulae are made up of interstellar dust, which consists of ionized and neutral hydrogen atoms and cosmic dust. Over time, some regions of the nebulae clump together and become dense. If the mass of this clump becomes larger than a certain mass known as Jean's mass, gravitational attractive forces win over the random turbulent forces of the dust cloud and the star begins to collapse, forming a protostar. Gravity keeps pulling the collapsing gas cloud and forms star like cores which keep getting bigger and denser. When the health when the pressure of this clump balances the gravitational pull, the process slows and we call this stage of the star a protostar. During this stage, the energy generated by the collapse of matter creates heat and pressure, causing the core of the star to reach temperatures of around 1000 Kelvin. However, these temperatures are not yet sufficient to trigger nuclear fusion, the process by which a star generates its energy. He- Here you can see pictures of nebulae captured by the Hubble and Spitzer space telescopes. The first two show nebulae, and the last one shows star formation in the center of the nebula. We'll now start following what happens after the protostar phase. As the core continues to collapse, it eventually reaches a point where the nuclear fusion is initiated, transforming the protostar into a main sequence star. Main sequence stars are crucial to the universe as they provide the light and heat that makes life possible on many planets that orbit them. The main sequence phase is characterized by the star shining with a constant luminosity and temperature, and its size remains relatively stable. The luminosity of the star is determined by its mass, with more massive stars being more luminous. The surface temperature of a main sequence star also affects its color, with blue stars being the hottest and red stars being the coolest. The lifespan of a main sequence star is also dependent on its mass, with more massive stars having shorter lives, while less massive stars can shine for billions of years. During this phase, the star generates energy through the fusion of hydrogen into helium, releasing a vast amount of energy in the form of heat and light. Once the hydrogen in the core of the star is depleted, it evolves into the next phase, the red giant. During this phase, the star expands, cools, and increases in luminosity, making it much larger and more visible than during its main sequence phase. The star's surface gravity also decreases, making it easier for it to shed its outer layers into space. When the star runs out of fuel, it expels its outer layers and forms a planetary nebula, a white dwarf, or a neutron star depending on its mass. The formation of white dwarfs takes place when a star has exhausted its fuel and is no longer able to support itself against the pull of gravity. The star will then cool and collapse under its own weight, forming a white dwarf. White dwarfs are extremely dense and small, with a radius of only a few thousand kilometers. They are extremely luminous and emit light in the ultraviolet and optical part of the spectrum. The temperature of a white dwarf can be several thousand Kelvin and decreases over time as a star cools down. White dwarfs are the remnants of stars that have exhausted their fuel, and they will slowly fade away over billions of years. They are important objects to study as they provide important clues about the evolution of stars and the universe. For example, the observed luminosity and temperature of white dwarfs can be used to estimate their age and to determine the rate at which they are cooling. They also play an important role in the evolution of binary star systems, as they can accrete mass from their companion star, leading to the formation of other exotic objects such as neutron stars and black holes. The path of a star from birth to death can be plotted on a Hertzsprung-Russell diagram, which plots the luminosity of stars against their temperature. The bulk of the stars lie in the middle of the diagram, and these are the main sequence stars. In the figure, we can also see the relation between color and temperature. The hottest stars are blue or white, while the colder ones are yellow or red. Our Sun, being a medium sized main sequence star, is present in the middle of the graph. The red giants are on the top right, and the white dwarfs are on the bottom left. The journey from the red giant phase to the final phase is marked by the loss of mass through processes such as solar wind and supernova. The latter is a violent process that occurs when a star has a mass greater than 4 times that of the Sun. The final phase of the star depends on its mass. If the remnant mass of the star is less than 1.4 times the mass of the Sun, it will evolve into a white dwarf. This limit was established by Indian American physicist Subramaniam Chandrasekhar, and it is now referred to as the Chandrasekhar mass limit. If the mass is greater than 1.4 times that of the Sun, the star will eventually become either a neutron star or a black hole, depending on its final mass. The remnant of the star contributes to the formation of nebulae, starting the cycle of star formation all over again. Gamma ray bursts, or GRBs, are powerful random explosions in the sky which release huge amounts of energy. Since their discovery, GRBs are perhaps the most mystifying phenomenon in astrophysics. A GRB can last for the duration of 10 milliseconds to a few hundred seconds. They can emit huge amounts of energy that our Sun will emit in its entire 10 billion year expected lifetime. Two classes, notably long GRBs and short GRBs, are considered to have different physical origins. Short GRBs are formed due to merger of binary neutron stars or a neutron star with a black hole. Such mergers produce killnovae. Long GRBs are formed during a rapid star formation, from a core collapse supernova, and during the death of a massive star. Now we come to what happens after a supernova. Although a star dies, if a red giant disperses into planetary nebula for massive stars, life continues even after the supernova, forming compact, exotic objects. Neutron stars and black holes are the final stages of massive stars, where the remnants of the star are compressed into incredibly dense objects. The final phase of a star's life is dependent on its mass. To understand the physics of black holes and neutron stars, Einstein's general theory of relativity, which is a theory of gravity, plays an important role. Neutron stars are formed when a star has between 4 and 10 times the mass of the Sun and undergoes a supernova explosion. The intense pressure from the explosion compresses the core of the star into a sphere with a diameter of only about 10 kilometers. But with a mass of 1.4 times that of the Sun, these neutron stars are incredibly dense. One sugar cube sized piece of the star, neutron star, would weigh as much as Mount Everest. Black holes, on the other hand, are formed when the remnants of a star have more than 10 times the mass of the Sun. The intense gravitational pull of the star is so strong that it collapses in on itself and creates a singularity, a point in space where the gravitational pull is so strong that nothing can escape it. Black holes are invisible, but their presence can be detected by observing the movement of stars around it. One of the most fascinating things about black holes is the concept of time dilation. Time dilation is the idea that time moves slower in strong gravitational fields. If you were to fall into a black hole, time would appear to slow down for you. But for those watching from outside, you would seem to freeze in time. Another interesting fact about black holes is the existence of accretion disks. Accretion disks are formed when matter, such as gas and dust, are pulled into the black hole by its intense gravitational pull. As the matter falls into the black hole, it heats up and emits intense radiation, creating a disk of light around the black hole. Neutron stars and black holes are fascinating objects that represent the final stages of massive stars. They are incredibly dense and have unique properties such as time dilation and accretion disks that make them an important part of our understanding of the universe. In conclusion, the final phase of a star's life is a complex and fascinating process. From the formation of white dwarfs to the formation of black holes, each stage of a star's life has its own unique characteristics and contributes to the overall evolution of the universe. Studying the different phases of a star's life provides us with important insights into the origins and evolution of the universe and helps us to understand the fate of our own star, the Sun.